Hello, everyone. Welcome to the April 7th edition of Math 262. This is the last material that will be covered before the midterm on Thursday. So, a couple reminders. Your mock exams will be due at the end of the day today. Your WebAssign is due tomorrow at the end of the day. That's Wednesday. And your exam will be on Thursday. That way, when it comes to Easter, you can do, not whatever you want over Easter, but you can do things with your family. So let's get started. So last time we talked about finding a Taylor series. And there's some guidelines for doing that. So the first thing you want to do when you're finding a Taylor series is to differentiate f with respect to x several times. And evaluate at c. So take a bunch of derivatives and then plug c into these derivatives. And what you want to do next is recognize a pattern. Okay. So from here, you want to use that sequence to form the Taylor coefficients. All right. And you want to determine the interval of convergence. Last but not least, we need to determine whether the series converges to F. Okay. So what I want you to do is I want you to use this technique to find the Taylor series for the natural log of x about c equals 1. And from that Taylor series, I want you to determine the radius of convergence. Okay. All right, so let's move on. Now, I want you to do that in your notes. So another example is, let's take a look at a Maclaurin series for a composition of functions. Okay, so let's look at the function, the cosine of the square root of x. And we're going to do a Maclaurin series. So c is going to equal 0. Well, let's start taking derivatives. So the first derivative isn't so bad. It's negative sine of root x times 1/2 x to the minus 1/2. The second derivative of x is equal to, well, let's take a look here, minus the cosine of root x times 1/2 x to the negative 1/2 times 1/2 x to the negative 1/2 plus negative sine of root x times let's see, I think this needs to be -1/4 x to the -3/2. Evaluating this at 0 is going to be very painful. And it will require limits. And L'Hopital's rule. Well, what can we do to avoid that? Well, we know that the cosine of a value, let's say z, is the sum from n equals 0 to infinity of -1 to the n, z to the 2n over 2n factorial. In other words, it's 1 minus z squared over 2 factorial plus z to the 4th over 4 factorial minus z to the 6th over 6 factorial, etc. So if I want to do the cosine of the square root of x, I just need to plug in root x for wherever z is equal to. So let's plug in root x in those expressions, and I get root x squared over 2 factorial plus root x to the 4th over 4 factorial minus root x to the 6th over 6 factorial. And I see that this becomes 1 minus x over 2 factorial plus x squared over 4 factorial minus x cubed over 6 factorial. So this series should just be equal to the sum from 0 to infinity, -1 to the n. The denominator is still 2n factorial, but the numerator is now x to the n. And so what this allows you to do is to calculate the Taylor series of this function right here, the cosine of root x. Trying to do it the old-fashioned way takes forever and will be terrible. So what you're going to want to do instead is to do a substitution where you substitute it in to the Taylor series for the cosine. Okay. So now that you've had some experience with Taylor series, in section 9.10, there's a list of some basic Taylor series. You don't need to have them memorized, you're welcome to, but you should know how these series were derived. That is, you should be able to figure out what they are on your own, like on an exam. So the functions that are there are 1 over x, 1 over 1 plus x, natural log of x, e to the x, sine of x, cosine of x, arctan of x, arc sine of x. You should be able to take and figure out what these Taylor series are using a variety of techniques that are described in the book. Okay. Okay, so today we're going to practice multiplying Taylor series. So this is essentially like multiplying polynomials, but you can do it infinitely. So we're going to practice finding the Taylor series of sine of x times the cosine of x. And we'll find the first few terms. So we know that the sine of x looks like this. It's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, ... And the cosine is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, etc. So how do I multiply two series like this? Well, what I do is I can create a little grid like this. So I can write the terms of my sine function over here. That's enough for there. That's all we need. Okay, and let's multiply. This is x. This is minus x cubed over 3 factorial. This is x to the 5th over 5 factorial. This is minus x cubed over 3 factorial. X to the 5th over 4 factorial. Excuse me, I messed up that denominator. This is x to the 5th over, let's see, that's 2 times 6 is 12. This is negative x to the 7th over 24 times 6. That's 144. Let's see, this becomes minus x to the 7th over, let's see, 120, that's 240. And this is x to the 9th over something big. Okay. So let's ignore these terms for now. So I'm adding up this series, and I see that what it should be equal to is x, and I see there's no degree 2 terms. The next term I need to combine are these 2 terms right here. Those are all the x cubed terms. So clearly, this is minus x cubed. And let's see, so it's x cubed, that's a half plus a sixth. So that's 2/3, I think. And then let's do the x to the 5th terms. So the x to the 5th terms are 1 over 120 plus 1 over 12 plus 1 over 24. And that should be 2/15. Okay, and then there are more terms. All right, so how do we determine what series this is? So what this is telling me is this is equal to, the first few terms of the series are x minus 2x cubed over 3 factorial plus 2 over 15 x to the 5th. And there are more terms. Where do you see this series coming from? What other series do you see? Oh, that's not 3 factorial. That's just 3. Excuse me. What other series do you see that's similar to this? Well, you see that this function for the sine looks pretty similar to that, but there's some key differences. And so if you remember your trig identities, you'll note this is the series of 1/2 times the sine of 2x. Because we can calculate this series using substitution. So it should be 1/2 the sum from n equals 0 to infinity of minus 1 to the n x, so it's 2x, excuse me, to the 2n plus 1 over 2n plus 1 factorial. And if you plug in some terms, you'll see that those two series coincide. All right, so I want you to do an example where you multiply these series out. I want you to do cosine of x times the cosine of x, and do the first up to degree 4. I want you to find all the terms of this series up to degree 4. Okay. So you can divide power series too. It's just like dividing polynomials. So let's find the series for the cotangent of x, which is the cosine over the sine of x. No, I lied. Let's do a different one. Let's do the tangent of x, which is the sine of x, over the cosine of x. So we see that the numerator is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, etc. And the denominator is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, etc. So we need to do our long division. We have the cosine part right here. And we have our sine function part right here. Okay, so we obviously multiply this by x first because we need to match up the leading terms. So this becomes, we need to subtract off x minus x cubed over 2 factorial plus x to the 5th over 4 factorial. You see we've multiplied everything right here by x, and now we need to subtract it off. And what we get is, I believe, let's see, we have an x cubed term, and it's 1/2 minus a 6th, so that's 1/3. And then we have x to the 5th here over, let's see, I believe this is over 30. Okay, we have extra terms there. So now we need to match up the leading terms again. So we multiply by x cubed over 3. And what we see we're going to subtract off is we multiply the thing underlined in red by x cubed over 3. And what we get is x cubed over 3 minus x to the 5th over 6. And then higher order terms. And we subtract that off, and we should get, let's see, I think 2 over 15 x to the 5th. And so clearly what we get is this should be plus 2/15 x to the 5th. And if we wanted more terms, we would need to include more precision. We would need to have more terms here and more terms here in the green stars in order to actually find out more terms of this series. So doing this long division, we found that the Taylor series for the tangent begins with these terms. All right. So I want to give you an example. And an example is I want you to do the sine of x over x. That one's pretty easy. And use this to see why the limit as x goes to 0 is equal to 1. So use this to see, and you'll see why this limit as x goes to 0 is just 1. All right, last but not least, we need to integrate. So integrating is a little bit interesting. So we can use this to approximate integrals of functions. So let's look at cosine of x squared. This is something we do not know how to integrate with our traditional techniques. So we need to use the Taylor series to help us. So we know that cosine of z is 1 minus z squared over 2 factorial plus z to the 4th over 4 factorial minus z to the 6th over 6 factorial. So if I plug in x squared into this, I get 1 minus x to the 4th over 2 factorial plus x to the 8th over 8 factorial minus x to the 12th over 12 factorial, and it continues on. So if I look at the indefinite integral of this function, it's like integrating this series. So I should get x minus x to the 5th over 5 times 2 factorial. x to the 9th over 9 times, excuse me, I made a mistake. It should be 4 factorial, 6 factorial. All right. And so if I evaluate this from 0 to 1, it's equal to this power series that I've written down. Evaluated from 0 to 1. And so I can use the first few terms to approximate it. I can use just these first 3 terms to approximate it. I get 1 minus 1 over 5 times 2 factorial plus 1 over 9 times 4 factorial. And this is equal to 0.9046. Now, this is an alternating series. So what this tells me by the alternating series test, it says that I'm off by at most this term right here. So remember, the alternating series test tells us that if I'm adding up terms in my series, my error term is less than the first term omitted. So that term is 1 to the 13th over 13 times 7 factorial, which is about 0.000107. That's really close. So what I want you to find out is how many terms would I need to add up to be within 0.000001. That's the same as 10 to the minus 6th. I don't actually need that many terms to be within 1/1,000,000th of the correct answer. And you're going to see how to do that. And so what you're seeing is that you can use other methods to approximate this integral, but using this Taylor series method, I can find very accurate approximations to within 1/1,000,000th by just adding up a few numbers. And so you can see now how your calculator can calculate some of these functions very quickly, integrate things very quickly using their Taylor series because of properties like this. All right, let me know if you have any questions. Good luck studying.